Today we will consider example 11, in which we will design another important filter. Design an all pass filter, all pass, that means it will pass all the frequencies. So, what is it going to be used for? Let us see later. With pole frequency at 1 kilohertz, now we have understood pole frequency and pole Q of 100. Sketch phase shift of the transfer function versus frequency, that is important. Here it is primarily used for obtaining phase shift variation with respect to frequency. So, we will see how such a network which passes all the frequencies without any attenuation or with same amount of attenuation or amplification, but will subject each frequency component to a certain phase shift. So, such a transfer function, second order transfer function, will look like this. The denominator is always represented in a standardized form. In the case of a filter, second order s squared by omega naught squared, omega naught being the pole frequency, q being the pole q. All right. So, this we have understood how this it is s here, not s, s squared, s plus 1. So, numerator now for all pass, that means all the frequencies should be transmitted, but there should be only phase shift. So, only sign wise it will change, the coefficients will be exactly same or of the same ratio, right. So, this is an all pass transfer function. The coefficients remain the same or they are of the same ratio. So, it could be that this is minus, this is plus, this is minus, or this is plus, this is minus this. That means, all the even functions will have the same sign and all the odd functions of s will have the same sign. Here of course, all will have positive sign. These are therefore the zeros. If you plot these zeros actually in the S domain for an all pass, you will see that there will be complex conjugate pair of poles if the Q is high, and there will be a pair of zeros, mirror image of poles. Okay. So, this is going to be in S domain, the location of poles for an all pass transfer function. What is it going to be used for is first something that we will discuss. Here, since if you take the magnitude, magnitude is unity throughout, or if there is a k factor here, it is going to be k throughout for all frequencies, because if you take the magnitude, this will give you a contribution of unity, because only change of sign occurs, right. Whereas, the phase shift is going to be offered by both poles as well as zeros. So, contribution to the phase shift is going to be there, and therefore, this is going to be very useful for obtaining phase shift. If you consider the phase shift at s is equal to j omega, omega equal to 0, the phase shift is 0, and ultimately again at s is equal to infinity, put s is equal to j omega and omega equal to infinity, the phase shift is becoming 360 degrees or 0 again, right. So, this will give you one full phase coverage of 0 to 360 degrees. If it is first order all pass, just for comparison, okay, first order all pass will be so, this will give you a full coverage from 0 to 180 degrees, 0 to minus 1, 180 degrees. Okay. A second order all pass will give you a phase coverage of 0 to 360 degrees. Now, that can be concluded, the pole alone can give you a phase shift from 0 to s squared means minus omega squared 180 degree, and addition will have 0 also contributing another 180 degree. So, the nature of variation of this phase with respect to frequency is same both for poles and zeros, because the coefficients are the same, and therefore, you will see that the phase shift varies all the way from 0 to 360 degrees, and you will note that if this is absent only due to pole, at s is equal to j omega, omega equal to omega naught, this gets cancelled with this, it is 1 over s, that is phase lag of 90 degrees. Now, this is phase lag actually, this entire thing can be. So, the 0 also contributes to 90 degrees at the same point, okay, phase lag of 90 degrees. So, 180 degree. So, this is going to be occurring at a frequency which is 2 pi into 10 to the power 3 omega naught f naught. Okay. So, this is going to be occurring at the pole frequency, this phase shift of 90 degree contributed by the pole, 90 degree contributed by the 0, 180 degree is going to occur at this, and it can be shown that the phase variation, that is delta phi by delta omega, okay, is maximum, okay, at omega equal to omega naught, and it is directly proportional to q. This I would like you to write down the phase phi for this, write down phi, okay, for this, and show that delta phi by delta omega is maximum at omega equal to omega naught and is directly proportional to q. That means, the slope at this point is going to be steep if q is very high. That is the function of q. If you make q very high, the phase will vary rapidly with frequency around omega naught. So, that in this particular case we wanted the phase variation to be maximum around 1 kilohertz, and we wanted the phase variation to be very rapid. That is why we have chosen the pole q to be 100. So, the purpose of designing, okay, this so called all pass circuit, so as to have the required phase variation at the required frequency, okay, is served in this manner. So, this gives you uniformly the phase varying from omega equal to 0 to omega equal to 360 degrees. So, this design of the circuit is for this purpose, to get this kind of phase variation. Now, let us see how this can be synthesized using the KHN network. This circuit is also called, let us say, universal active filter, or also state variable filter. Different people call it different. Okay. So, how do we therefore get this all pass function? We know that band pass, low pass, high pass outputs can be obtained at the outputs of these 3 operational amplifiers in the case of the state variable filter. So, we have to simply add these, because high pass comes without any sign change, low pass comes without any sign change, band pass already has a sign change. Okay. In our expression, if you see, right, high pass comes without any sign change. So, high pass is actually equal to 2 into 1 minus alpha s squared by omega naught squared divided by the same denominator s squared by omega naught squared plus s by omega naught cube plus 1. this is high pass. Low pass is going to be 2 into 1 minus alpha divided by the same denominator, where omega naught is equal to 1 over R C, this we already know, and Q is equal to 1 over 2 alpha. This is required to be made equal to 100. So, alpha is 1 over 200. This is to be made equal to 2 pi into 10 to power 3. So, R if I select as 10 K like last time, C becomes 15 nanofarad. This we had already calculated earlier. So, with that kind of thing we have high pass here like this, low pass here like this, and band pass is minus 2 into 1 minus alpha S by omega naught divided by the same denominator. So, what do I want? I want to simply add high pass with low pass and band pass. Only band pass has to be added with suitable modification of the coefficient, because band pass coefficient should not be the same as the coefficient of low pass and high pass, right. Here the coefficient of this thing is 1, here it is S squared by omega naught squared, which is 1 again, right. Here it is 1 over Q S by omega naught. So, you can see here we have the coefficient here same 2 into 1 minus alpha, 2 into 1 minus alpha, minus 2 into 1 minus alpha. So, we can simply add. So, that is the arrangement. This is a summing amplifier. I am adding low pass, okay, with high pass and band pass with a modified coefficient. Here it is going to give inversion for both low pass and high pass, just minus 1. Okay. So, we get a coefficient here which is going to be minus 2 into 1 minus alpha, because of the inversion for both of this, minus 2 into 1 minus alpha into S squared by omega naught squared plus, let us say, plus 1 divided by the same denominator, S by omega naught whole squared plus S by omega naught Q plus 1. This is what we are getting at the output of this. Okay. If we simply add this one with minus sign, then this one we already have taken out 2 into 1 minus alpha with a minus sign. So, that will be again minus. Okay. So, because it is originally itself minus, so it becomes plus here. So, S by omega naught comes there, 2 into 1 minus alpha has been taken out, and here the coefficient is n, right, R divided by R by n, that is n. So, n can be made equal to 1 over Q. So, this is the output, let us say V naught 4. So, this is equal to V naught 4 by V I. So, V naught 4 divided by V I is that, and that design is over. We have already made Q equal to 100, omega naught equal to 2 pi into 10 to the power 3, and if I make n equal to 1 over Q, I would have achieved the all pass filter design. So, this is the usefulness of this summing amplifier here. It can therefore make you locate the 0 anywhere on the S plane. Now, we have located the 0 here. Okay. So, you can locate the 0 anywhere you like, and the pole gets fixed by omega naught and Q. So, let us now consider another important part of active filters, that is simulation of inductor. Now, this comes into picture. Inductor, for example, in the micro miniaturization becomes a very difficult component to deal with, the coil. in monolithic integrated circuit it is not possible to fabricate it at all. So, almost all circuits which are to be made out of monolithic IC require that inductor be not existing. Suppose therefore, we want to simulate such an inductor using resistors and capacitors and active elements. How is it possible? Now, this circuit which is called a gyrator. Gyration means rotation, right. What it means is a capacitor has a certain relationship with voltage and current, and that relationship is made use of in order to change this voltage to current relationship for the simulated component, that is the inductor. So, Zi here should become inductive. So, let us suppose that this is Vi. I am going to analyze this circuit and we will see how to analyze therefore op amp circuit in a very simple manner. If this is Vi, if this is a circuit which is supposed to work with negative feedback, then this has to be Vi. This we said null. If this is Vi, this has to be Vi, and if this is so, this is Vi, and the current in this is Vi by R. If that is the current in this Vi by R, the same current should be flowing through this. So, the potential across this R is also going to be Vi. So, this is going to be Vi. That means, this is twice Vi. That can be easily concluded also by the fact that this is nothing but a non-inverting amplifier of gain equal to 1 plus R2 over R1. R2 is equal to R and R1 is equal to R. So, the gain from here to here should be equal to 2. So, this is 2 Vi. If this is 2 Vi and we all already know that this is Vi, this has to be Vi. So, the current in this has to be Vi by R. This current cannot go anywhere else other than into the capacitor. So, the drop across this has to be Vi by R into SC with this kind of thing. So, the voltage here is going to be this Vi minus the drop here this is the voltage here. I am applying Vi here, this is R. So, the potential across this is this Vi minus this Vi, those Vi get cancelled, plus Vi by SCR. So, potential across this is Vi by SCR, and the current through this is in this direction, this divided by R. So, the impedance in is nothing but Vi divided by, let us call this II. This is equal to Zi. So, Vi by II is Vi by SCR square. So, this is nothing but SER square. So, impedance is SCR square, which is not anything other than that of the inductor. So, L simulated is equal to C into R square. So, any such circuit which is terminated by a capacitor and sees an inductor is called gyrator. This is one such circuit which is able to use a capacitor for simulating an inductor of magnitude equal to CR squared. One thing you should note, however, is that this inductor is between this point and ground. Therefore, this is a grounded inductor. What is the use of this? Let us therefore go to the good old networks that we have understood earlier in the networks course. This is what is called as a tank circuit which can store energy, that is being excited by, let us say, a Vi through a resistance Rs. So, if I now take the output here, V naught divided by Vi is the transfer function of this, is always equal to V naught and Vi. The conductance linking that. This is one way to write down easily this conductance linking the output with the input, divided by the total admittances, right. So, 1 over Rs plus Sc plus 1 over Sl. This is the transfer function, easy way of writing. The conductance or admittance linking the source with the output divided by the summation of all admittances. So, we get here this as Sl by Rs divided by multiplying by Sl throughout S squared Lc plus Sl by Rs plus 1. Now, this is rewritten according to us as normalization, just as we did in the case of our KHN filter or universal active filter or state variable filter. This is put as natural frequency S squared by omega naught squared plus S divided by omega naught into Q plus 1. So, omega naught is equal to 1 over root Lc, and that is by comparison you can see omega 1 over omega naught squared is equal to Lc, omega naught is equal to 1 over root Lc, and we have omega naught q is nothing but Rs divided by L. So, you can write down Q quality factor as Rs divided by L into omega naught. So, please remember here this is the conventional definition for Q of a parallel resonant circuit. Q is always equal to the resistance shunting the parallel resonant circuit divided by the inductive impedance. Or this is also equal to Rs into omega naught C, because omega naught C is equal to 1 over omega naught L. So, this is equal to Rs by L divided by omega naught 1 by omega naught is equal to root L into C, this is Rs into root C divided by L. So, this is known to you for a passive network. So, you can therefore fix the center frequency of this band pass. This is called a band pass filter. So, how will the response look like? The center frequency omega naught is going to be 1 over root Lc, and at resonance this is going to be 1, because put S is equal to j omega naught, in fact the numerator is also going to be S by omega naught q, because it is same as Sl by Rs. So, at resonance this particular thing becomes infinite resistance, and output will be equal to input. So, this is unity, and the bandwidth obviously that is at 0.707 okay, value. This bandwidth corresponds to omega naught divided by q by definition. So, all these things are known to you from your networks course. Now, if I want such a circuit without using an inductor, I simply use this, remove this grounded inductor and use this gyrator circuit. So, what happens here? Just remove this. This will simulate an inductor I know of magnitude equal to C into R square. Then I put another capacitor, because I have to put another capacitor. Let us say that also is C, right, and I put a resistance which is R S. So, now at this point, if I put V, let us say we will call this V I, right, then this V I prime is going to be my V naught here, which is going to have a transfer function like this. If I take the output here, this will be V I prime, this to distinguish it from this V I. This will be twice V I prime. So, it will be again band pass. The output here also is going to be band pass. So, you can as well take the output here, because here it is buffer. That means, you can load this without affecting the Q of the circuit, right. So, but it is better to take the output here, which is going to give you twice V I, that means twice S by omega naught Q, okay, S squared by omega naught squared, S by omega naught Q plus 1 is got here. And what is Q? Let us find out. First of all, let us find out what omega naught is. Omega naught for this is 1 over root L C. Root of L is equal to C R squared. C R squared into C. This is equal to 1 over R into C. Very simple, just like the case of state variable filter. So, if I fix R and C's accordingly, I can fix omega naught easily. Next, we would like to know what Q is. Q is given by R S into root of C by L, which is C into R squared, which is nothing but R S by R. So, this is a very simple design. R S has to be equal to Q into R. Okay. R S value should be equal to Q into R, and omega naught has to be equal to 1 over R C. So, let us now consider an example, so that this problem is clear, of simulation of inductor. Okay. Design a band pass filter using gyrator, okay, at 1 kilohertz center frequency with a Q equal to 100. So, how do we proceed with this? The circuit is the same. Omega naught is given as 1 kilohertz, that means 2 pi into 10 to power 3. this is equal to 1 over R into C. For a change, we will take R as 1 kilo ohm. Last time we took it as 10 kilo ohm. Then C will be larger, 150 nanofarads. Right? Earlier it was 50 nanofarads, now 150 nanofarads. Then RS has to be 100 times 1 kilo ohm, 100 K. So that finishes the design of the band pass filter. Gain at the center frequency is going to be 2, because we are taking the output at this point. Gain at the center frequency is going to be 2 instead of 1. So actually for our circuit now, this will be, if you take the output there, 2, and this is going to be 2 pi into 10 to the power 3, and this is going to be 10 hertz. So this is a very simple design. Now we have understood what is meant by this particular thing of design has to be given as filter with gyrator. This has to be given example. What is the example? 12. So please make that correction. Now let us come to an important topic, harmonic oscillator, which we have already touched upon. When we discussed state variable filter, we said solution of d squared V naught by dt squared plus gamma V naught equal to 0 is nothing but V naught equal to some a sin omega t plus phi. So it is a harmonic oscillator. This is a very important thing. This might have been taught you in mechanics already, this simple pendulum. So here in using L and C, it has been taught you that this is nothing but a tank circuit. If ideal L and ideal capacitor are connected like this, and you pump in certain amount of energy, that energy is retained in the form of oscillation, and that oscillation frequency is 1 over 2 pi root L C. All of you know. How do we obtain this solution? It is very simple. If L and C are connected like this and V is the voltage here, node voltage, then C dV by dt is the current in the circuit, which is also same as plus 1 over L integral V dt. So current entering and current leaving. So from that, C dV by dt plus 1 over L integral V dt is equal to 0, or we can write this as like this, or d squared V by dt squared plus V by LC equal to 0. This is the same equation that we get. This, if this is V naught, let us call this V naught, so that we are consistent with our symbol used in state variable filter. So you get the same equation, d squared V by dt squared plus gamma V naught equal to 0. Solution of this is nothing but what? Some Vp sin omega t plus some phi. Omega naught is the resonant frequency, is equal to 1 over root LC, root of gamma. That is known as the frequency. In mechanics, you might be using some k or something like that there. So omega naught is equal to root LC. This as a resonant circuit which can sustain sinusoidal oscillation with certain amplitude. It does not tell anything about the amplitude, it depends upon the energy that is pumped into it. So, that will be sustained throughout with that magnitude, it will not decay or grow, right. So, this is the case. If let us understand this, d squared V naught by dt squared, okay, plus you get V naught by LC equal to 0 gives you a sinusoidal oscillator, right. If this coefficient of here dV naught by dt, which we had earlier put as some alpha or something like that, okay. So, if this is 0, then it is a harmonic oscillator. If this is negative, okay, the poles will be lying on the right half of the S plane and the amplitude of oscillation will keep on growing, right. The growth is characterized by e to the power some k times t, k being positive. This is what determines that. So, if alpha is positive, then it will decay and go to 0, right. So, basically speaking, right, this alpha is going to determine whether it is going to be growing with respect to time or decaying with respect to time. If alpha is 0, it is constant. If alpha is negative, it will decay. If alpha is positive, it will grow. So, this is the way you have studied in networks. So, it will grow like this if alpha is positive. If it is negative, it will decay, ultimately become equal to 0, otherwise it will remain constant. So, this property is important to understand in the case of oscillators. So, how can I therefore say that in practice, right, this circuit definitely is going to have inductor with some loss component in it. So will the capacitor have some loss component. If I can represent this loss component in terms of a resistance dissipative, that is the thing, then in this equation, okay, the current that you have to add will be, okay, sum of all currents V naught by Rp. Okay. In fact, it was C dV naught by dt, okay, V naught by Rp plus 1 over L V naught dt. Now, dividing throughout by C, this will be getting C, this will be getting C. This therefore gets modified as, okay, dV naught by dt plus V naught by Rpc, right, plus dV naught by dt. Because once you differentiate, you get that, plus V naught by Lc equals to 0. So, how to make it an oscillator now? Because this is going to cause decay of whatever oscillation amplitude that exists. So, ultimately it will become 0. So, that means I will have to connect another resistance across this, right, whose value is negative, so that it cancels with this. So, that means this will then be modified at d squared V naught by dt squared plus 1 over Rp, okay, minus 1 over R into 1 over C dV naught by dt, okay, plus V naught by Lc equal to 0. So, I require a negative resistance to make the resistance equal to infinity. When will it happen? When R is equal to Rp. So, and then I make R equal to Rp. You notice that if R is greater than Rp, the oscillation decays, right. If R is less than Rp here, okay, oscillation grows. When exactly R is equal to Rp, oscillation amplitude is remaining constant, amplitude remains constant. This basic principle has to be understood in terms of time domain. In terms of frequency domain, what does it mean? This will have, okay, roots lying on the left half of the S plane, okay, because of this being positive, okay. If this Rp is positive, if effective resistance is negative, it will have the roots lying on the right half of the S plane. If R is exactly equal to Rp, the roots will be lying on the imaginary axis, then it is a harmonic oscillator. How do we have to design oscillators? Because initially there will not be any amplitude. When you switch on, there will not be any amplitude. A practical oscillator should have amplitude building up. So, building up. Of oscillation. If oscillation amplitude has to be built up, what should be the case? The poles of the system should lie initially on the right half of the S plane, or in this case R should be initially less than Rp, then it keeps on growing. Then I should change the value of R, okay, such that R is exactly equal to Rp at the required amplitude I desire, okay. That is what is called amplitude stabilization. At the required amplitude, make R equal to R. So, this is the strategy which is adopted in every harmonic oscillator, okay, so that the oscillation starts. Okay. Invariably, it will be pretty close to the imaginary axis, but it will be on the right half of the S plane. Then gradually, if this is the S plane, somewhere here, let us say, and it will come and lie exactly on the imaginary axis, right. This is how poles have to move of the system, which is as amplitude builds up, the poles must move this side and lie exactly on the imaginary axis at the required amplitude of oscillation. So, this covers the basic theory of amplitude, okay, stabilization for any oscillator. Okay. Now, we have discussed what is called as two terminal oscillator, okay, negative resistance oscillator it is called, wherein I have put an inductor and a capacitor practical value whose loss component is represented as Rb, Rp, and I am putting a negative resistance. So, now I would like to know how to simulate negative resistances. We already know how to simulate inductor. So, we have capacitors anyway, these are going to be lossy. So, let us now try to understand how to simulate negative resistance. This simulation process is very simple. Let us once again assume that we can use the op amp. If this is Vi, if this is V I and I connect a resistance like this to ground and that resistance is R, right. It is a positive resistance. How do I make out? Because a current of V I by R will flow in this direction. When will it be a negative resistance? When a current of V I by R flows in the opposite direction. So, that is a very simple. If this is V I, so if this is to see a negative resistance and I put R and it has to see a current which is in this direction, which is of magnitude V I by R, obviously the potential here should be, this is V I and the potential across R should be V I, but in the opposite direction. That means the potential here has to be twice V I. Is this clear? This is twice V I, this is V I. So, the potential difference here is going to be plus here minus here of V I, and the current will be V I by R in this direction. So, how do I get a gain of 2? I can put R and R. So, this simulates a negative resistance of magnitude R. So, I want to simulate a negative resistance of magnitude how much? R P. So, I simply put here R P, right. So, this simulates a negative resistance of magnitude R P. So, if I connect this circuit between this point and ground and I use a practical L and C with loss component R P, then it will invariably go into oscillation. If I do not want to use an inductor, I can simulate that inductor using the gyrator, right. So, let us look at that circuit of ours, that is the gyrator circuit. How will it look like? In fact, we had used this kind of resistance there, if you remember. So, the first circuit was an amplifier with gain of 2. So, if this was V I, this was twice V I. Then we put an integrator R here like this, and we had connected another resistance from here to here, and it was simulating an inductor between this point and ground whose magnitude L was equal to C into R square. Now, I want the capacitor to come here. If the capacitor is connected like this, now will it oscillate? Unfortunately, we have assumed that these are ideal operational amplifiers with infinite gain. That is how we are able to derive this as C R square. But actually, if you take finite gain, which is non-infinity, then you will see that this inductor will be shunted by a resistance of magnitude which is dependent upon A naught into R. Okay. So, there will be a loss component. Even otherwise, the capacitor also will have a loss component. So, necessarily I must put a negative resistance of suitable magnitude to make it go into oscillation. Otherwise, the oscillation will invariably die. So, how do I now create a negative resistance? It is very simple now, from V I to V I. So, I put a resistance here which is R P. That will compensate for the so called loss component which is already existing, whose magnitude is equal to R P. So, this circuit will invariably burst into, you can therefore start with very large value of R P, keep on reducing it. At a particular point, you will see that the whole circuit will burst into oscillation. Here there is nothing limiting the amplitude. So, it will go up to the supply voltage, right. So, it will burst into beautiful sinusoidal oscillation at frequency omega naught equal to 1 over R into C. The poles therefore lie exactly on the imaginary axis. So, this is what is called as a gyrator oscillator. Right. uses only resistors and capacitors, and you can vary the capacitor and make the frequency vary. Okay. So, this is the basic principle of such oscillators. We will discuss in the next class other types of oscillators, which normally cannot only be represented in this manner, but also can be represented in another manner, that is straight away as synthesis of a second order differential equation with dV naught by dt being absent. Okay.